Hello, and welcome to our presentation on Eaton Supercharger's analysis of potential automation. The Eaton Supercharger facility in Athens, Georgia has assigned us with the task of investigating whether adding a robot to a manual operation will improve their cost savings and productivity. In the current system, there is one operator who moves the parts from station to station, which takes 20 seconds. He is paid $50 per hour. We have been tasked to find the cost and time savings that would result from adding a Fanuc robot arm. We must calculate the break-even time for installing the robot while not exceeding the design limits. These results need to be broken down into a 1, 2, and 3 times factor of safety. We are also asked to calculate the velocity and acceleration at J6 at a specific instance. Currently, the Eaton Supercharger facility is paying an employee $50 an hour to transport 30-pound and 120-pound parts from one station to another. It takes 20 seconds to move one part, and the employee is a constant expense. It is given that the employee works 21 hours per week, which we calculated to be 1,092 hours annually. Therefore, the cost of the employee is $54,600 a year.
While evaluating this switch with a 1, 2, and 3 factor of safety, we apply these factors of safety to the lift capacity of the robots. We focused on 3 all-purpose Fanuc robots that would give us factors of safety close to our desired numbers. We obtained the data required for these robots directly from the sheets provided by Fanuc. In order to find the prices for these robots, we requested quotes directly from Fanuc for each robot, but we did not receive a response. We therefore had to use the estimates given to us by Motion Controls Robotics, a controller company that works directly with Fanuc products. That company gave us the price ranges listed here, and we will use the higher end of these price ranges in order to simulate the worst case scenario for our break-even predictions. In order to find the increase in production from our robots, we had to first map out the required motion of our robot arm. To do this, we modeled first the overhead view, as you can see in the upper left-hand corner of this slide. We used the system description to find the rotation in degrees required to move an object from station A to station B. We then doubled this rotation in order to get the rotation for one complete cycle. We then did the same thing from the side profile of our robot. We calculated the rotation required per each of the 2 joints in order to clear the 1 meter tall station divider. We then adjusted these rotations again to achieve the required rotation per cycle.
From the product data sheets, we compiled the capabilities of the robot options in terms of their maximum angular speed around each axis. Using the required angular movements needed to complete the given task, we were then able to calculate the time required by each arm segment to complete a full cycle. The final time needed is then limited by the longest individual movement time and is recorded here. Also, the instantaneous velocity of the tip of the robotic arm is found at the height of its movement, directly over the median. At this point, the velocity is one-dimensional and found by multiplying the angular speed and the radius. The acceleration of this point was not found, as the manufacturer does not provide any information on their product's acceleration capabilities.
So in the end, we found that the M710 IC70 model with a factor of safety of 1 has a break-even period of 1.56 years, while the R2000 IC100P model with a factor of safety of 2 has a break-even period of 2.01 years. Last but not least, with a factor of safety of 3, the R2000 IC165F model has a break-even period of 2.38 years. It is evident that as the factors of safety and price of the robotic arm increase, the break-even period also increases. Clearly, there is a trade-off between safety and how long it takes to break even. So the right robotic arm to go with depends on how the managers and engineers at Eaton value these 2 things.